Alright, Assalamu alaikum. So from this video onwards, we'll be starting off with integration. And obviously we're talking about A2 level integration at this point of time. We'll start off with some of the very basic things about integration. We all know that integration basically is, what is integration? It's actually the reverse process of differentiation. And we know that differentiation is actually the process of obtaining derivatives or gradient functions. What do I mean by a gradient function? A gradient function is an algebraic expression such that if we put any value of x in that expression, it is going to give us the numerical value of the gradient of the tangent drawn at that point. For example, if I have a curve y is equal to x cubed add 3x squared, we know that the derivative of this point of this curve would be 3x squared add 6x. Right, I'll call this thing a derivative or a gradient function. Why? Because if, let's say, I want to find out what is the numerical value of the gradient when of the gradient at x is equal to 2, let's say, then all that I have to do is plug in x is equal to 2 in this expression, and I'm going to get the value of the gradient of the tangent at the desired point. Now, since integration is the reverse process of differentiation, it means that the raw material for integration is definitely going to be a derivative, right? Now, just like we represent differentiation with either dy upon dx or f dash x or y dash, we also have a notation for representing integration, and that is this weird hook, right? So this is the sign of integration, right? Now some very important terminologies. Uh, the raw material for integration is, as I just said, the derivative. However, we have studied at AS level that it's not always the derivative that's being integrated. For example, I might be interested in finding the area bound by a curve and the x-axis. So what do? I integrate the equation of this curve and not the derivative. And then I apply the limits, and that gives me the area between the curve and the x-axis. So the point that I want to make here is that it's not always the derivative which is being integrated, because obviously there are many other uses of integration as well, and not just obtaining the equation of a curve from the expression of its derivative. So to make things more general, I won't call it the derivative, right? Instead, the thing that I am integrating is called the integrand, right? The thing that is being integrated is called the integrand. And now, since integration is defined as the reverse process of differentiation, to indicate, to give an indication of this definition, what we do is that after the expression that we are supposed to integrate, that is the integrand, we write down dx here. If the integrand is in terms of x, if it is in terms of t, we would write dt. Likewise, we would change this x according to the variable being used here, right? And the end product of the process of integration gives us something called an integral, right? So now let's review the formulae that we studied at AS level, because obviously those formulae will be coming in handy at this level as well. So now we will keep this thing in mind at all times, that integration is the reverse process of differentiation, and what we will be doing to obtain the formulae, the desired formulae for integration, we will actually see the derivative, we will see the processes involved in obtaining that derivative, and then we are going to reverse those processes and obtain the formula for integration of that particular expression. Right, so let's start off with the most basic formula of integration, and that is for the expression, let's say y is equal to a to the power of n. Now, the derivative of this is n times a to the power n take away 1. Right? So this was the derivative. Now, what did we do to obtain the derivative? The first thing that we did was that we multiplied the algebraic part. Alright, I have just made a small mistake. I should write x here. So I'll make it x here as well. Right. So the first thing that I did was that I multiplied the variable part with the initial power. What I did was I multiplied the variable with initial power. Then what I did was in the next step, I decreased the new power was basically 1 less than the old power, right? So the second thing that I did was that the new power was equal to the old power, take away 1. So now, in order to obtain the formula for the integral of x to the power of n, what will we do? We are going to reverse these processes. So, the first thing, let's talk about the power. In differentiation, the new power was equal to the old power, take away 1. Therefore, if we reverse this thing, the new power in this case would be old power add 1, right? So here we have x to the power n add 1, right? Now let's talk about this step written in red and how we're going to reverse this. Now what we did in differentiation was that we multiplied the variable with the initial power. So let's reverse the steps. We multiplied in while obtaining the derivative, so we will divide while obtaining the integral. And what will we divide it with? The new power. Right. So while obtaining the integral of this function, what we'll do is that we are going to divide this by the new power, which is, as we can see, a total opposite of what we did in differentiation. Right. So this is the algebraic part here, and then we add the constant of integration. Right. So this is the first and the most basic formula. Right. Now, why do we have to include this constant integration here? The answer is simple. See, uh, let's take three expressions. Y is equal to x to the power x squared add 3, y is equal to x squared add 5, and y is equal to x squared add 9. Now, if I find the derivative in each case, it is going to give me the same thing, that is 2x. Now, if I reverse the process of differentiation in an attempt to reach to the original equation again, I integrate all these, this is going to give me x squared, which means that these constants are actually lost in the process of differentiation such that they cannot be recovered by integration just as it is. Therefore, to indicate that yes, there might be a constant as well which was lost, which was irretrievably lost during the process of differentiation, as an indication of that constant, we add a plus c here, and this plus c obviously can be evaluated if we have some other information with us. Right. So this is the first formula of integration which we learned at AS level, and we also learned that this formula has one very important limitation, which is that for this formula, n cannot be equal to -1. Right. So which means that for all powers of x, I can use this formula except if the integrand has a power of -1. In that case, this formula is going to fail. And in future videos, we are going to learn how are we going to integrate when x has a power of -1. Right. So this is the first formula. Now, let's come to the second formula that we learned at AS level. The second formula basically was the reverse of, alright, let's take this, ax plus b to the power of n. Now, if I want to differentiate this, I'm going to get n ax at b to the power n take away 1 times a, right? So what have I done here? The first thing, I multiplied the bracket by the initial power, right? Multiply by initial power. Second step, I decreased the initial power by 1. Decrease initial power by 1. And the third step was, I multiplied all of this by the derivative of the bracket, right? So, we multiply by derivative of the bracket. So now, in order to obtain the integral of this, we are going to reverse all the steps. That is, firstly, we will the new power would be the old power add 1, right? So we get ax add b to the power of n add 1, right? Then we multiplied the bracket by the initial power. This time what we do is, we are going to divide by the new power. And now finally, about this a here, which was the derivative of the bracket. What we'll do is that we are gonna divide this by the derivative. We are going to divide, in order to obtain the integral, the final step would be to divide this by the derivative. Now a question here might arise that if we are reversing everything, then why don't we divide by the integral of the bracket? Right? This might be a very valid question, and this is a very good question if you have this question. I'll repeat the question once again. The question is that if in order to obtain the integral, we reverse every single step, then why are we dividing the variable part by the derivative of the bracket and not by the integral of the bracket? The answer to this question is the fact that the raw material for integration is the derivative, which means that, see, this is my raw material, right? And since this is the raw material and this is actually the derivative, in essence this would be the derivative, right? And so it means that if this is the derivative, this would have been obtained by multiplying by the derivative of the bracket, right? So when we are reversing differentiation, we will have to divide by the derivative and not by the integral. I'll repeat the answer to this question again. See, the raw material for integration is the derivative, and derivative is obtained by multiplying the bracket by the derivative of the bracket. So when we are obtaining the integral by reversing every step of differentiation, we actually have to reverse the multiplication that we had carried out. And the reverse of multiplication is division, right? And since we had initially multiplied by the derivative, in order to reverse the effect, you have to divide by the derivative and not the integral. I hope this is clear. If you still have any questions, you can ask in the comments, and inshallah I'll try to answer this. And then obviously here comes a plus c. And again, this formula has the same limitation as the previous one, that is that it applies to all powers of n except -1. Right. So far, we have just reviewed the stuff that we have already studied at AS level. Now let's come to the stuff that is in the A2 syllabus. So in A2, we are going to study about integration of trigonometric functions. We are going to study about integration of exponential functions. We are going to study about the integration of logarithmic functions. We are going to study some more advanced algebraic functions as well. And we will also be studying about how to integrate combinations of these. For example, I might be having an integrand consisting of a product of a trigonometric function and an algebraic function. Likewise, I might be having my integrand is such that we have an exponential function being multiplied by a trigonometric function. Right. So, in this video, I'll just be discussing the most basic formulae of integration of trigonometric and exponential functions. We'll study about the integration of logarithmic functions later when we study integration by parts. So as of now, we'll be doing more videos on trigonometric functions as well. Right now, I'm just discussing the most basic the most basic integrals of trigonometric functions. The more advanced ones will be covered, inshallah, in specialized videos on differentiation on integration of trigonometric functions. We'll be having 2 to 3 videos which will be dedicated to integration of trigonometric functions. Right. So, from our knowledge of differentiation, we know that the derivative of sine x is equal to cos x. So, if we reverse the process of differentiation, that is, if I put an integration sign here and an integration sign here, so this is cancelled out, right? Integration cancels out the differentiation and hence indicated here. So, the integral of cos x comes out to be very simply sin x add c. This is the first formula. Right. Now, let's talk about the derivative of cos x. And this is negative sin x sin x, right? Now, let's reverse the process of differentiation again. So here comes the integration sign. Integration cancels out the differentiation. And here we have cos x is equal to the integral of negative sin x dx. Now I can take this negative sign outside the integral, right? So we have negative sin x dx is equal to cos x. And therefore, we get the second formula, which would be integral of sin x would be negative cos x add c, right? So we are done with 2 of the formula. The third formula. We know that the derivative of tan x is sec squared x. So essentially, if we reverse the differentiation, we are going to get the integral of sec squared x dx as tan x add c. Now, what is the integral of tan x? For this question, we'll have to wait a bit. In one of the future videos, when we start off with integration of the functions of the type f dash x upon fx, at that point of time, I'm going to tell you how to integrate tan x. At this point of time, we're not discussing that, right? So the integral of tan x comes later. But at this point of time, we interestingly can discuss how to integrate tan squared x. This is interesting, right? that we don't know how to integrate tan x, but we can still study about how to integrate tan squared x. And the answer to this lies in trigonometric identities. Now, see, we have studied this earlier in the chapter of trigonometry that 1 add tan squared x is equal to sec squared x. Therefore, tan squared x becomes sec squared x, take away 1. So I can replace my integrand here with sec squared x add 1. Sorry, take away 1. Dx. And this obviously can be written as sec squared x dx add 1. Sorry, I'm making this error time and again. Take away like 1 dx. So this becomes tan x, take away x, and c. Therefore, the integral of tan squared x dx is going to be this. Right. You're not supposed to memorize this formula. If you know the method behind obtaining it, well and good. However, it's strongly recommended that you do memorize Formula 1, which is this one, Formula 2, which is this one here, and Formula 3, because these will be forming the basics of all integration of trigonometric functions that we'll be performing later in this chapter. Alright, now let's elaborate on this a bit. If we go back to the chapter of differentiation, there we learned that the derivative of functions of this type were a cos ax add b, right? Which means what we did was that we first differentiated the trigonometric function and kept our angle unchanged. Then we multiplied the function by the derivative of the angle, right? Once again, what we did was that we differentiated the function. We know that the derivative of sines are cosines. Therefore, with the unchanged angle, I first wrote cos ax plus b, and then I multiplied the trigonometric function with the derivative of the angle. So, when I want to reverse this process, what I'll do is, instead of multiplying by the derivative of the angle, I am going to divide it by the derivative. This gives me three formulae, which are actually extensions of just this thing. No rocket science here. That is, the integral of cos ax plus b would be 1 upon derivative of the angle times sine of ax plus b at c. Similarly, sine ax plus b would have an integral of 1 upon a, negative 1 upon a, cos ax at b at c, and sec squared ax at b would have its integral as 1 upon a tan ax at b and c. So that's all about about integration of trigonometric functions at our level, right? So in these formulae, if you notice, we have omitted a number of things. Number one, all trigonometric functions except sec squared obviously have powers 1, right? So we don't have cos squared, we don't have sine cubed or anything of that sort. If we do have powers applied to trigonometric functions, then the method of differentiating them of integrating them is going to be different, and that we are going to study when we'll delve deeper into integration of trigonometric functions. But as of now, the most basic integration of trigonometric functions does not involve any powers. That is, the power of the function is 1. The second thing is the angle. The angles in all three cases are linear functions. That means the formulae that we have studied here will apply only if the angle is a linear function and not if it is any other function. This is actually similar to what we studied here in this case. You must have been told at AS level that in these cases, this formula applies only when the stuff inside the bracket is a linear function. This is in contrast to differentiation, where no matter what function we had, we could still differentiate it this way. In integration, things are a bit limited. I was once going through a book, and the author of that book was probably in a very philosophical mood. He said that just like many things in life cannot be reversed, similarly, almost all functions are differentiable, but not all functions are integrable. And if they are integrable, it is done through very awkward methods. So, just like this formula for integration, which you learned at AS level, did not apply if we had anything else in the bracket except for a linear function. Likewise, the formula that we have studied here for integration of trigonometric functions won't apply if the angle is any other function instead of a linear function, right? So that is the basic of trigonometric integration. Now, let's come to integration of exponential functions. From our knowledge of differentiation, we know that if I have e to the power of fx, its derivative is going to be the function itself multiplied by derivative of the power. So it's very easy to understand that if we reverse this differentiation, what will happen is that we'll just be the integral of f derivative x, the integral of f e to the power of something would be 1 upon derivative times e to the power of fx at c. Now here's another limitation here. The power must be linear, right? So we'll be more specific here. That is, if we have e to the power ax at b dx, its integral would be the function itself divided by derivative of the power, right? So that's it, right? So that's all for this video. We'll just make a summary of all the formulae that we have learned so far. The first formula was integral of x to the power of n dx is equal to n add 1 upon, right? The second formula goes something like this. Which is ax add b to the power of n add 1 upon the new power times derivative of the bracket add c. And I told you why are we dividing by the derivative but not the integral? Because we want to reverse a differentiation, and the derivative was obtained by multiplying by the derivative of the bracket. Therefore, we have to divide by the derivative and not the integral. Then integral of cos ax add b would be 1 upon a followed by sine Then we have sec squared x, which gives me, and then lastly, we studied about exponential functions, which was that if we have an exponential function e with power, the linear power, then its integral would be 1 upon derivative of the power times the function itself. So that's it for this video. In the next video, we are going to study about what to do when we have uh, we'll study about how to integrate functions of this sort, right? So far, that's all. These formulae, these 6 formulae that I have mentioned here, these are a must to learn, and these must be on your fingertips because these formulae are going to form the basis of the many other videos on integration that are yet to come, right? So until the next video, Assalamu alaikum.